Good morning. So, in the last class, we looked at computational learning theory and we looked at situations where a learner sees a certain number of examples, outputs a consistent hypothesis, and we derived bounds on how many examples the learner has to see so that a consistent hypothesis is a pack hypothesis. So, today we will continue our discussion and look at the situation where the hypothesis output by the learner has non-zero error on the training set, and then we will look at a few worked out examples. So, we want to in the last class we have seen that in the finite hypothesis case where the learner outputs a consistent hypothesis, what value of m is required. Now, today we will look at how many samples will be required to guarantee a pack hypothesis, and we will explain what we mean by this, where the learner outputs a hypothesis which has some error. There is a sample error which is output by of the output hypothesis. Now, what we want to do is that we want to find the guarantee that the actual error, the true error of the hypothesis f over the distribution d. F is a hypothesis which is output by the learner, which may have an error given by error df, where d is the sample. This is the sample error and this is the true error. So, we want the probability that the true error is less than equal to the sample error plus epsilon. We have earlier seen that normally the true error will be greater than equal to the sample error, and we want that the true error is not so much different from the sample error, that is, true error is less than equal to epsilon plus sample error for a given epsilon. And we will find out that if m is the number of training examples with respect to which you have tested, you have come up with the hypothesis, then this probability is less than equal to e to the power minus 2m epsilon square. And we want to ensure that the best hypothesis that our algorithm outputs has error bounded in this way. So, we consider that any one, suppose the hypothesis that the learner comes up with has an error df, this is the sample error, and we want to find out the probability that there exists any hypothesis whose true error is less than equal to this is less than equal to h times e to the power minus 2m epsilon square. This is for a single hypothesis, this is where there exists any hypothesis at all. And from this we can derive the bound by algebraic manipulation, that in order to ensure that the number of examples required must be greater than equal to 1 by 2 epsilon square times logarithm h plus logarithm 1 by delta. So, if you have this many number of examples, then the hypothesis which comes up with a training error of x will correspond to a hypothesis whose true error is less than equal to epsilon plus x. So, just to summarize, in consistent case we found this bound on m, this value of m. In the inconsistent case we find this value of m, and we can compare these two equations. So, here in the consistent case we came up with m greater than 1 by epsilon log h plus log 1 by delta. Here we come up with this value of m. Okay. So, we see that there is a lot of similarity between these relations, but in this case, in the inconsistent case, you require larger number of examples, larger by a factor of 2 by epsilon in order to give this guarantee. What is the guarantee? The guarantee is that the true error is no more than epsilon error, epsilon plus sample error. Okay. Now, now let us look at an example of the first case. So, suppose we look at a particular hypothesis class. So, our hypothesis class is conjunction of Boolean literals. These are also called monomials. Suppose x1, small x1, small x2, small xn are your features. These are your features. So, examples of Boolean literals are x1 and x2 bar and x4, x2 and x3 bar and x4 bar, x2 bar and x7. These are examples of conjunction of literals. Now, this is our hypothesis space. How many, what is the size of this hypothesis space? There are n literals in a particular hypothesis. That literal may occur in the positive form, may occur in the negative form, or may not occur at all. So, for each literal, there are 3 ways of it appearing in this formula, and there are n literals. So, the size of the hypothesis space is 3 to the power n. If we take this particular hypothesis space, the size of the hypothesis space is 3 to the power n. And if we plug it in here in the equation that we have, then what we get is m greater than equal to 1 by epsilon log of 3 to the power n plus log of 1 by delta, and log of 3 to the power n is just n log 3. Now, we can put values for epsilon and delta, and given the number of features, we can find out the value of m, and these are some of the values that I have worked out. If epsilon and delta are both 0.05, then if you have 10 features, then you require 280 examples. If n is 10, epsilon is 0.05, delta is 0.01, then you require 312 examples. If epsilon and delta are both 0.01, then you require 1560 examples. If epsilon and delta are 0.01, n is 50, it requires 5954 examples. And these values are coming from this formula, and this result holds for any algorithm which, given a training set, can find a consistent hypothesis. And it is up to you to design an algorithm which processes a training set and finds out if there is any consistent hypothesis. If there are many consistent hypotheses, your algorithm will come up with one of them. One such algorithm we will just discuss very quickly, that can come up with a conjunction of Boolean literals given a training example, is called FindS, and I will quickly go through the algorithm. So, here we have a concept learning task, and we have 6 different attributes: sky, air temperature, humidity, wind, velocity, water, temperature, forecast, enjoy sport. So, enjoy sport is our target variable, and these are our input attributes. Now, a conjunction of constraints, a conjunction of literals is our hypothesis space, and a conjunction can be represented by, you see, for every attribute in a particular hypothesis, that attribute may occur in the positive form, may occur in the negative form, or may not occur. If it does not occur, any value of that attribute is acceptable. So, I put question mark when any value is acceptable, and otherwise I specify whether it is there in the positive form or negative form. Phi means no value is acceptable. So, this is a representation of one such hypothesis, which says the x1 can be anything, x2 must be cold, x3 must be high, x4, x5, x6 can be anything, right. So, this is one particular hypothesis. The most general hypothesis is one where any attribute can take any value, and the most specific hypothesis is one where no value is possible. Now, what the finder's algorithm does is that it initializes small h is our current hypothesis, it initializes small h to the most specific hypothesis in the hypothesis space, in this case 5, 5, 5, 5, 5, 5. Then it takes a positive training instance, and for each attribute a I in the hypothesis, if the constraint a I in H is satisfied by x, we will do nothing. Otherwise, if it is not satisfied, we will replace a I by the more general constraint satisfied by x. For example, if a I was given as true and it is not satisfied, then we will put a I can be anything. Finally, after processing all the positive examples, we will output the hypothesis H that we get. So, suppose you are given this training set and you run the algorithm, then initially H1 is the most specific algorithm, most specific hypothesis where all attributes, none of the attributes are permissible. Then after you see the first example 1, where sky is sunny, temperature warm, humidity normal, etc., then H2 becomes sunny, warm, normal, strong, warm, same, which agrees with the first training example. It is the most specific hypothesis that agrees with the first training example. Then you bring in the second training example, and the second training example has humidity is high, which is not agreeing with the current hypothesis. So, humidity you set as question mark, which is the more general form. Then we look at the next training example, and you find out that water is not agreeing, water and forecast are not agreeing. So, you put these things. So, this is the final hypothesis that you have. H4 is sunny, warm, question mark, strong, question mark, question mark. Okay. Now, this is the finder's algorithm, which given a set of training examples finds a consistent hypothesis, and if more than one consistent hypothesis exists, it will come up with the one which is most specific. And according to our theory, for this particular hypothesis, we can have this relation. The relation states that if we look at these many number of examples, then we can produce these guarantees. If your hypothesis space is all possible Boolean function, the size of the hypothesis space, if you have n attributes, is 2 to the power 2 to the power n, which we have already seen. In this case, m will be given by this relation, m greater than equal to log of 2 to the power 2 to the power n plus log of 1 by delta into 1 by epsilon. And if you put some values of epsilon and delta, for example, epsilon and delta are 0.05, n is 10, you require 14,256 examples. But if n equal to 20, you require 14.5 million examples, and n is 50, you require 1.56 into 10 to the power 16 examples. So, if the number of attributes is large, the number of examples required is exponential in n, which makes this problem infeasible. With this, we stop today. Thank you.